be talking about the heat transfer mechanisms, calorimetry, and thermal expansions. So basically, thermal expansion of solids. So and then I will be making a separate video on sample problems on all these topics. So basically, there are four different types of heat transfer mechanisms: conduction, convection, radiation, and evaporation. But basically, we'll be considering conduction, convection, and radiation in this chapter. So these are all on this in this picture. As you can see, all these are examples of the transfer of heat through different mechanisms. So the first one is the conduction. So if you are soldering something on electrical circuits, you are directly transferring heat to the circuit. So that's done through the conduction. Convection. This is so if you leave your drink, a hot cup of coffee, it will finally cool down, and it's mostly convection. And this is radiation, and this is evaporation. So, but like I said, actually we'll be talking about the first three one. So what is conduction? Is the transfer of thermal energy directly through the physical material, and without the flow of the actual material. So what happens in conduction is, so suppose if you heat a rod and the other end is connected to the ice, right? So heat will transfer from high temperature to low temperature, right? In this direction, it transfers from high to low temperature. And what happens is, actually when you heat at this end, the atoms and molecules, which are modeled as connected by many atoms with spring-like forces, intermolecular forces. So when you heat it up, these molecules will vibrate, oscillate, energize with more and more kinetic energy, and this will transfer the energy to the neighboring molecules, neighboring atoms, and so on. And the net result is the transfer of heat from one point to other. But as I mentioned before, the molecules itself actually do not travel from one point to other point. They just oscillates with energy. And so the conduction through any material is given by this law of conduction. So it's called law of conduction. So it says the rate of transfer of heat, which is Q over T. This rate of transfer of heat we call Q over T is equal to Ka delta T over L. So where K is the thermal conductivity of the material, which is a constant for the given material. Different materials have different thermal conductivity, and A is the area of cross section. Delta T is the temperature difference between these two temperature bands, and L is the length. So, and then if you want to calculate, so this is the power actually, right? Because this is the energy transfer per second. So, and if you just want to find the energy transfer for a given time, so then you just multiply by T. So this is called law of conduction. This is the main equation in conduction that we'll be using. So you also need to know something called temperature gradient. So if you have one end at hot and one end at cold end, so you have a temperature gradient. Temperature gradient is simply the change of temperature with distance, with length. So if this bar is well isolated, with insulator, you have the temperature gradient is uniform. The temperature decreases from hot to cold end gradually, like this. You have a uniform temperature gradient like this. You have a uniform. But if this is not well isolated, you have the temperature falls exponentially with distance. So this is without insulation, as you can see, and you have a non-uniform temperature gradient. So temperature gradient is something, the change of temperature over distance. So in this table you can see this is the table of the thermal conductivity of different common materials that we will be using in our numerical problems. So you can clearly see some materials like diamond, silver, copper, iron these are metals, good conductor. They have very high thermal conductivity, whereas these are the insulators. So you can see wood, carpet, and air. They have very low thermal conductivity. That means they are insulators. These are conductors, these are insulators. So let me ask you a question. Why does a tile floor feel colder than the carpet at the same temperature? So this example, this dog is probably perhaps trying to cool down his feet just by putting his feet in on the tile floor. And the reason is because if you see the tile floor has a good thermal conductivity compared to the carpet. Carpet is almost poor conductor, it's an insulator. So when you toss the tile floor, actually the rate of conduction of heat through your body to the floor will be higher, and that's why you feel colder actually. Even if carpet and floor are at the same temperature, right? Because of the rate at which the heat transfer. And the same thing actually, the second question, exactly same. If you touch a metal and plastic rod, what happens? So metal feel colder than plastic rod, right? Even if they are at the same temperature, same region. So that's it. That's all about conduction, and then I'll be showing you many sample problems. So second type of transfer of heat is convection, and convection is the transfer of heat through material, by actual transfer of the molecules, actual transfer of the particles of the medium, and it mostly takes place in fluid. Okay, it mostly takes place in fluid. It's mostly transfer takes place in fluid system. So what happens is, so for example, if you are boiling a water, what happens? The water molecules in contact with the oven, they get warmer, and the lighter, warmer fluid rises up, while some of the cooler surrounding cooler fluid takes its place, right? And in the process, heat is transferred by the convection. So then this is called convectional current, and this process will continue until the whole volume of water gets the same thermal equilibrium. And same thing, so if you have a hot drink, actually the thermal convection through air is taking place here. Air is fluid here, and this is a heating element. Actually, this is a heating water element. It's you can clearly see it's a thermal graph. You can clearly see the warm water is rising up, right? And it will be replaced by the cool molecule, and this process will continue until the whole water will have same temperature, and this is called convection. Mostly takes place in fluid means air and liquid. So air is a poor conductor, we know from the number, right? But it can transfer thermal energy effectively, very effectively, by convection. It cannot transfer heat energy, through conduction, but it can effectively transfer thermal energy through convection. Because why? Because air molecules can move. Air molecules can move easily. And this example, in this bird, penguins, right? They have feathers for right, and it works as an insulation, and that traps the air molecules in small spaces, and that actually stops the convection. And basically, the use of jackets, and is to stop convection, actually reduce or stop the convection, and that will stop the heat transfer by convection. And something using the fan and motor, you can do the forced convection to transfer, for ventilations. So the next transfer of heat is by radiation. So the radiation is the transfer of heat energy through electromagnetic waves. Okay, electromagnetic waves, a kind of electromagnetic wave is called radiation. And because the main origin of electromagnetic waves is atoms itself, atoms, molecules. Because when the charged particles in atoms oscillates, they radiate electromagnetic wave. So examples are the light itself is electromagnetic wave. It has a broad spectrum. So, and it can even travel in vacuum, actually. So radiation can even travel in vacuum. So through this radiation method, one can actually transfer heat without any material medium around it. That's how we get the solar radiation from sun to earth. So radiation doesn't need any material medium because electromagnetic waves can travel even in vacuum. This exchange of heat occurs via emission and or absorption of the electromagnetic waves. And in all these pictures actually are examples of the transfer of heat through radiation process. So here in this portion, actually, this is the infrared picture thermograph. You can clearly see, right, different parts of the body are radiating at different temperatures. This is a false temperature graph. So red means is transferring heat at so radiating at faster rate, where blue is at lower rate, and same thing with the dog. So here's a brief example of electromagnetic wave. It has a broad spectrum, but the only visible light the human eye can detect, can see from our brain, is this visible spectrum, red to blue, red to violet. In terms of wavelength, is 400 to 700 nanometer. So 700, and this is 400 nanometers. But spectrum, well, spectrum extends well beyond that range, actually. So beyond the red, you call infrared, and far below that is microwave, and then radio waves. Radio waves are a very low frequency or very long wavelength. And above violet or blue is called ultraviolet, and then X-ray, and these are very energetic waves. So this is an example of the electromagnetic wave spectrum. This is the narrow band. This is the visible spectrum. So this is the visible spectrum. And there's a law of radiation that we'll be using, and it's called Stephan's law. And it says the rate of emission of radiation, which is Q over T, right? The rate of energy loss over time, which is the rate of emission of radiation, power, right? You can also call power, is given by this formula based on the Stephan's law. It says, so E sigma AT4. So basically it is proportional to the fourth power of the absolute temperature. That's what Stephan's law said. So where P is the power, which is power means it's Q over T, right? Q over T. E is the emissivity of the surface. It depends on the surface. It's a measure of how effectively it can radiate. So the value of E is between 0 and 1. 1 means perfect emitter or absorber. It depends on the material. That will be given to you. Sigma is called Stevens-Boltzmann constant. It's always a constant number. Right? That will be given to you. A is the surface area, not cross-sectional area, because the surface area. For example, if it is a sphere, right, the surface area of a sphere will be 4 pi r square. And T is the absolute temperature. Temperature must be in Kelvin, absolute scale. So this is called Stephan's law. So here's in summary, here's if you are just sitting down somewhere and your body will be losing heat energy through different mechanisms, 4 different mechanisms as we talked. So for example, 30% will be evaporation, and 40% will be through radiation, 27% will be through conduction, and about very little, actually, only 3% will be through conduction, right? Let's continue the rate of loss of heat by radiation. So this formula is only for one object. If you have just one hot object, the rate of emission of radiation is given by this formula. But what would be the net heat? Net heat transfer, right? If you have 2 objects, so let's say that the net heat transfer will be given by rate of emission minus rate of absorption. Because if you are radiating energy through your body, because you are surrounded by because you are since you are in a room, and room is also emitting energy, right? And which your body will absorb, right? You are radiating energy, but at the same time you are also absorbing energy from the surrounding object. So what will be the net rate of transfer of heat by radiation? So, and then it's given by rate of emission minus rate of absorption. So the formula is P net will be E sigma A T4 minus TS4. So T is the temperature of the body itself. TS is the ambient temperature, it's the surrounding temperature. Okay, so this is the formula we'll be using to solve some numerical problems. So here's the example problem I will be showing in a separate video. And there's it's called space blanket. It is engineered to reflect and retain about over 80% of the radiated body. And the space shoot actually also uses this technique, actually, because this shiny surface keeps the radiation inside the body. And other more examples are the only mechanism by which Earth can transfer heat to space, right, is by radiation, because above 200 miles above there's no atmosphere, there's no actual material medium actually. So the only mechanism by which Earth can, transfer heat into the space is by radiation. And this is the actual infrared picture taken from space, from International Space Station. You can clearly see the oceans. This Atlantic Ocean is really warm compared to this northeast actually. So it's a global convection. So heat is being transferred from warmer ocean, Florida coast, right, to the more cooler, and this process will continue actually, right. This is called global big scale conduction. So, and one more example on radiation is, so your house also may lose actually energy effectively by radiation, because you can clearly see if you have a low quality window, right, you'll have enough heating bill actually. And then you can fix that problem by replacing this single glass window by double glass window. And you can show by calculation, now you will actually, the heat loss will be reduced by over 90% actually. You can save the rate of loss of heat by through conduction over by 90%. So next is Newton's law of cooling actually, and we're going to use Newton's law of cooling idea in one of our lab, actually cooling lab, that I will be assigning you soon. So if you bring two objects at two different temperatures, heat flows from higher temperature to lower temperature object, right, until there is a thermal equilibrium. That's the universal principle. That's the very natural thing, right? And Newton's law of cooling states that right, the rate of loss of heat, the rate of cooling is directly proportional to the temperature difference between the object and its surrounding, and that's all. That's called Newton's law of cooling. So here D is, let's say D is the temperature difference between the body and the surrounding ambient temperature, and the temperature difference changes, exponentially over time, right? And that's how it behaves. So if you plot the graph, then D, right, versus T, where remember D is the temperature difference between the body and the surrounding, and this difference will exponentially change like this. So that's what the Newton's law of cooling said. So where D naught is the initial temperature difference, right? Initial temperature difference, and this K is called cooling constant, which we can measure from experiments, and which depends on number of factors such as insulation, the amount of substance you put, etc., and then for the given experiment is the constant. And this is how we do the experiment actually. So you take a water in a beaker, put the lid, and then you put the temperature sensors and connect it. You can take the temperature data over time, temperature versus time data with Logger Pro, software, and then you can do analysis. So how do you find the cooling constant experimentally? So this is our beginning equation, right? And then you divide by D naught, and then take the log, because if you want to get rid of this exponent, you have to take the log both sides, because log of E is 1, so you get this, and K will be natural log D over D naught divided by T, and negative. So that's the technique we'll be using to find the cooling constant, in our experiment. And so here examples are the use of heat sinks. So these aluminum heat sinks in motorbike, and this heat sink in processor cooling, in computer, is actually that the use of heat sink actually increases the cooling rate significantly. Okay, the main purpose of using the heat sinks, in different devices are because that will increase the cooling constant, cooling rate, this K, the value of K very rapidly, I mean significantly, which we can test it in our lab. So so I'll be showing separate example problems. So just to continue, so the next topic on this lecture slide is calorimetry. So calorimetry has to do with the measurement of heat energy. So what factors actually of the given substance affect the transfer of heat. So we'll be learning the measurement of heat Q. So as you know, if two substances at two different temperatures are brought into thermal contact, heat flows from hot substance to cold one, right, until they reach the common final temperature, and that we already know that. It means after reaching the thermal equilibrium, heat will stop transferring if the whole system is thermally isolated. So we assume that the whole system is thermally isolated, right? So for example, cooling a hot drink with ice, the hot drink will lose heat, right? And the ice will gain heat. If the system is properly isolated, so the whole system is supposed properly isolated, then principle of calorimetry says heat loss by drink must be equal to heat gain by the ice, right? Because of conservation of energy. So that's called principle of conservation of, that's called principle of calorimetry. Heat lost is equal to heat gain. And this is the example, right? And heat loss is equal to heat gain, so that means Q1 is equal to Q2, and negative sign means because it's a loss, one is losing heat, one is gaining heat, so that's why the other one should be opposite, so that's why you have a negative sign. So that's why here then from equation Q1 plus Q2, right, will be equal to 0, and you can extend that principle to many systems, not only two systems. So if you have more than two substances are in thermal contact in an isolated system, then you can say that the total net heat transfer Q1 plus Q2 plus Q3 and so on will be 0, right? And how do you calculate this Q, which is the heat transfer, right? So it depends on many factors. So heat loss or heat gain can be calculated just by using this formula. So Q is mc delta T. So what is m is the mass. The C is a constant for a given substance. It's called specific heat capacity of the given object, and delta T is the final temperature minus initial temperature. Is the change in temperature. So that's why your C, which is the specific heat capacity of the given substance, is Q over this. So how do you define the specific heat capacity? So here's the definition. So specific heat capacity of a substance is the amount of heat required to raise the temperature of 1 kilogram of substance by 1 degree Kelvin or 1 degree Celsius. So that's how we define the specific heat capacity. And here's the specific heat capacity for different substances. So different substances have different, specific heat capacity, especially so you can clearly see here, right? So some substances are really big, some substances are really. So water has in this list, water has got the the highest specific heat capacity, right? Which is almost 4200. It's unit is joule per kilogram per. So what's the meaning? What's the meaning of specific heat capacity of water as 4190 joules per kilogram per degree Celsius? So that means it means you need almost 4200 joules of energy, right? It will be required to raise the temperature of 1 kilogram, right? Remember, 1 kilogram of water by 1 degree Celsius. So that's how we define specific heat capacity by definition. So now the next is heat subtransformation. So heat subtransformation is the heat required to change the phase of the substance. So phase means usually any object has three different phases: solid, liquid, and gases. So when you heat a substance, so at some point it will melt, right, or eventually it will evaporate. So during this phase change, so you won't see any change in temperature. The temperature remains constant during the phase change, but it's absorbing heat. It's radiating heat, it's absorbing heat, but temperature is not changing. So then that means you cannot use this formula anymore, right? Q mc delta T you cannot use. So for heat of transformation change in phase, you will have to use a second formula, and it's called heat subtransformation, or latent, also called latent heat. It's just L times M or M times L. So M is the mass, L is called specific heat of latent heat of transformation. Okay, and that will be again different for different substances. So here's an example of latent heat of transformation. So if you try to warm up, try to raise the temperature of ice and water mixture, right? And if you put a thermometer, temperature sensor, and if you record the temperature versus time, this is how it will change. It won't be a linear correlation, So initially the ice is warming up. Once the ice has melted completely, then during ice melting, actually the temperature remains constant, which is 0 degree, which is the melting point of ice, right? Temperature doesn't change during the phase change where ice is melting. And then again, water is warming up, And once all the water has reached 100 degrees Celsius, now it will change its phase from liquid to gas, right here. And you get a flat line actually. Temperature doesn't change. This is 100 degrees Celsius. This happens at 100 degrees Celsius, right? And this happens at 0 degrees Celsius. So these are called heats of transformation. And you'll have to use, remember, you'll have to use this Q is ml formula, not MC delta T. And here's the table for specific latent heat, L, right? L for different substances, and L has two parts actually. L has one is L of F, which is the latent heat, specific heats of transformation for fusion, and one is specific heat of transformation for vaporization. V means vaporization, F means fusion. So we'll be basically using this data actually. So this and that. And you can clearly see melting ice and water always have 0 degree, exactly 0 degrees Celsius. Temperature doesn't change. So here's some examples. So the very last topic on this slide is thermal expansion. So basically thermal expansion of solids. So as you know, it's a common sense, right? Increasing the temperature of a solid causes it to expand. All right, and it's not very difficult to understand this at microscopic. So at microscopic level, again, materials are made up of atoms, molecules, trillions of particles, right? And they are connected by spring-like forces like this. And when you heat it up, actually, these molecules will actually will vibrate, oscillate with more energy, right, like this. And the mean distance between these, the average spacing between these two atoms increases. And that's the main cause of thermal expansion of solid. As you can clearly see, right, as you increase the temperature, the spacing between the average spacing increases. And usually, as you know, such materials are very useful. So for example, mercury and alcohol expands or contract very rapidly, right, and that's why they can be used in temperature thermometry. So here's the formula for linear expansion, thermal expansion of solids. So linear expansion is the expansion of length, expansion in length, right? So for example, if you have a very thin rod, thin means its thickness should be very small compared to its length. So if you have a thin rod and if you try to raise the temperature of the rod, right, its length increases in both sides. And so the increase in length is given by this formula. The thermal expansion of in length is given by this formula: alpha L naught delta T. So delta L is the change in length, is the final minus initial length, right? Delta T is the change in temperature, and L naught is the original length, and alpha is a constant for the given material. It depends on the material. It's called coefficient of linear expansion. So this is the formula we'll be using, to solve some numerical problems. Okay, so thermal expansion of any length, the linear expansion is given by this formula. This is just the empirical formula. And similarly, volume expansion is the expansion in volume. So for example, if you have a sphere, right, at some initial temperature, and if you heat it up, so the whole sphere volume will increase. And this increase in volume will be very small actually. You can't even see in real life. But actually even 1% or 2% actually you can calculate actually. And again, same formula, the increase in volume or thermal expansion in volume is given by this formula. Delta V is given by beta V naught delta T. So delta V is the change in volume or expansion in volume expansion or cubical expansion. Delta T is the change in temperature. V naught is the original volume, remember. And beta is a constant for a given substance. It depends on, it's different for different substances. It's called coefficient of volume expansion, cubical expansion. So that's about the volume expansion. So and here's the list for volume expansion and alpha expansion coefficients, for different substances, and you can clearly see, right? So beta has to be exactly 3 times alpha, okay, because it's a cubical expansion. So and these are the values you will be given. And this is the actual data actually for different substances. So you can clearly see the thermal expansion increases almost linearly with temperature within certain range of temperature. And here's some simplifying this formula. You can simplify this formula. Sometimes it's useful to use this different form of formula. But delta L is LF minus L naught, right? Initial, final minus initial, and then you can bring this L naught to the other side. This becomes this, and L naught you can common factor out, right? L naught, and this is the second form of formula. So final length is equal to initial length 1 plus alpha delta T. So similarly, final volume is equal to initial volume 1 plus beta delta T. So when you solve the actual numerical problems, sometimes this second form of formula will be very useful. And here's some examples. So this thermal expansion of solid will be only 1 or most probably 2%. But for a big structure, something like that, big bridges, building, even 1% put out very big stress actually in the structure. So if you don't consider this thermal expansion in your design, it may actually bring a big structural damage actually in your structure. So here's the example actually of the buckling, bending of the railway track. So this railway track has no gap. The modern railway tracks have always some thermal expansion gaps, just like this. And if you don't put that, and because of weather changing weather, significant changes in weather can bend actually. And this is basically because of the thermal expansion. Right, and so even in concrete, actually, you must have this thermal expansion joints. So though solid behave, regularly, so water has actually very strange property. So between 0 to 4 degree, only from 0 to 4 degree, water actually expands on cooling, actually, not on heating. Because if this is the density graph, density of the water as a function of temperature. So you can clearly see density increases, right, until if you heat it up from 0 to 4 degree, right? So that means its volume actually decreases if you increase the temperature because density is increasing. So it has got the maximum density, the water has got the maximum density at 4 degrees Celsius. So 4 degrees Celsius has the highest density, it's the heavy water. That's the reason actually water always freezes from top. So even during the very peak winter, actually the pond and the lake never freezes at the bottom, and because all the heavy water, 4 degree water, settle down at the bottom, and water, always freeze from the top, and all the aquatic animals. That's the reason actually the life is possible. Aquatic life is possible. And here's some conceptual examples. If you have a stubborn tight lid, actually just run a hot water a couple minutes actually, and then you can easily open this actually after some time. And this is an example of the differential expansion because you have aluminum cap, right, and the glass, and they expand quite differently. So that because of that differential expansion, and the aluminum cap expand more than the glass, so then you can open it very easily. And here's some example problems.